let's start. So today is the last lecture of GIT3. And what I want to do today is to give you a criterion, useful criterion to decide when a point is stable or semi-stable, and then give you some examples, some applications of the criterion. So last time we were talking about orbits, and I need some general results about them. So let's start with a basic proposition. So let's pick an algebraic group, any algebraic group, acting on a variety. X. So everything defined over an algebraically closed field, and everything reduced there. So, so you have the notion of orbit, definition. So let X be a point. So the orbit of X is the set that I would denote this way of all the translates of the point. So simply like that, as a subset of X, we're going to see that it has a structure of subvariety, so it's locally closed. That's the notion of the orbit, and then there's the notion of the stabilizer of X is Gx. So it's a subgroup of G of those elements that fix my point. Okay? Of course, the condition of multiplication and everything is algebraic. So this is more than just a subgroup, it's an algebraic subgroup. So it's a closed subvariety, yes? Yes, yeah, so all points also closed. Right, I want to, yeah. Huh? Yeah, everything over k bar, yeah. So, yeah, so all points are going to be closed in this talk. Okay, so, of course, there is a connection between stabilizer and orbit. And their dimensions are related. So, proposition, so in this setup here, general setup, we have that the orbit is locally closed, as I mentioned. We have that the dimension of the orbit is complementary to the dimension of the stabilizer. That is, the sum is the dimension of the group. And 3, we have that, that will be important, that if we choose the set of points such that the dimension of the orbit is at least n, then this is open in X for every n. Okay? So let me prove this. So to prove one, we consider the orbit map, which is a map that goes to here. Right? We want to consider this as a map of variety, so let me take the closure here. So what happens is that, of course, this map is dominant, since the image is the orbit. And for a dominant map, we know that there is an open subset, right, such that U is contained in the image, which in this case is the orbit. Okay. Now the orbit and its closure, they are invariants. So when you pick an element in the group, it acts upon here, and when I look at the image of U, I then get another open set, because G is an automorphism of disclosure. Right? And in fact, since the orbit is transitive, if I pick the union of all these translates, I get the orbit. right? So you see that the orbit is a union of open subsets of OX bar, so it's open. Okay? So OX is locally closed. That's the proof. For the second, I will assume that the G is irreducible. Not necessary, but you have to do some reduction. And I'm not going to worry about it. You can do that. So assume G is irreducible. Then we look at this map here from G to OX, right? And since it's dominant, there is a fiber such that the dimension of the fiber is the difference between the dimensions of G and the orbit. Okay? So there is such a fiber. And what happens is that all these fibers are, in a sense, equal. So the fiber here is just a lateral class of the stabilizer. Okay? So that's easy to see, right? If I pick an element in the lateral class and apply to X, then Gx disappears and you get Gx. I mean, this G times X. Okay, so that means that the dimension of the fiber, whatever fiber you pick, is the dimension of the stabilizer. Okay? And then you plug in here and you get this, these two. Okay. As for 3, what you do is you consider the following map that takes Gx to Gxx. And then what you get, if you look at the inverse image of a point in the diagonal, what you get is just the lateral class. You get Gx times X. Okay? Now, if you look at Xn, this is also the set, since we have this equality here, right? It becomes also the set where the dimension of Gx is less or equal than, well, I have to plug in here, dimension of G minus n. Right? So using 2. Okay? So it's the set of points such that the dimension of the fiber, which is the same as here, is less or equal than the dimension of G minus n. But then this should be open by semi-continuity. So semi-continuity of the dimension of the fiber. Okay? So this is the general result that I needed, and the notions. So let's go back to our setup of the last lecture. So I'm going to look at a projective variety. And I'll look at linear representation of a certain group, algebraic group, such that X is G invariant. That is, the action of G induced on Pn leaves X invariant. Okay? So this is what you get when you have an action on X that is linearizable. And I'm picking a linearization. Okay? So last time we defined a subset, the subset of semi-stable points. And these are given by the following condition. These are the points such that there is a D positive and an F homogeneous invariant of degree d such that f of x is non-zero. Okay? So that's XSS. And then we have the set of stable points. Which is the set given by the same conditions, but with an additional. So again, the same thing. But you ask something further. You ask that the orbits in XF, so XF becomes an invariant open subset, and I ask that the orbits here are closed. Closed in here, in XF. Okay? So it's a further condition. So you get a subset. Of course, you see that these are invariant subsets, right? Because I'm picking F invariant. It's also easy to see that the F's that appear here, right? So what you have is that, for instance, from here, I mean, you have that in this situation here, that XF is contained in XS. S. Okay, so the whole principal open subset is contained in the semi-stable locus, right? Because of the condition given, right? All the points in XF satisfy this condition. And here the same, because I'm asking that all the orbits, not just the orbit of the point, but all the orbits are closed. So in this situation here, if F satisfies this condition, then also the whole principal open subset is in XS. Okay? So these are open. These conditions are all open. Okay. Proposition. Assume G is reductive. Then I'm going to look at this set, XSM, the set of points in XS, such that the dimension of OX is exactly the dimension of G minus M. Right? And this is both open and closed in XS for every. Yeah. Okay. Usually such a thing would be locally closed, but we're talking about an action of a reductive group. And in fact, what we're going to use is just the fact that there is a geometric quotient for XS. So what are the importances of these open sets is that there is a good quotient for the semi-stable locus and a geometric quotient for XS. Right? Because I can consider this space here. So similar definition, but greater or equal. And by the proposition that I just raised, we know that this is open. Is open. Okay, so that's general. You don't need any condition on the group. But as I mentioned, for XS, there is the geometric quotient. So if I pick geometric quotient, then the fibers are the orbits. So you see that this guy here is the same thing as the inverse image of what I'm going to call this way. And this is the set of points such that the fibers have dimension, at least dimension of G minus N. Right? Because the fibers are the orbits. So this set here is closed, because I'm asking the dimension to be greater or equal than something. So it's closed in Y. So the inverse image is also closed. So you see that this is both closed and open. And then so is this set here with similar definition, because it's the complement of a set like this. And so the intersection is also closed and open. Okay? Okay, so something very special happens here. And in fact, usually you just get one of these sets. That is the whole stable locus. Usually all the fibers, all the orbits have the same dimension. For instance, if XS is irreducible, so if this guy is irreducible, for instance, if X is irreducible, because this is an open subset, then it's just one thing for some M. Okay. So you have a decomposition of the stable locus, a disjoint decomposition, and then you have equality in this situation. So in a lot of applications, what happens is actually that the dimension of the orbit is maximum. That is, this M is equal to 0. Remember that the dimension of the orbit being equal to the dimension of G means that the stabilizer is finite, right? And a lot of the objects that we want to parameterize have finite automorphism group. So you get that in a natural way. So let's then concentrate on this case where M equals to 0. And then we have a nice result here. Again, assume G is reductive. Let me pick a point which is already in the semi-stable locus. If it is also in the stable locus, then the orbit is closed in the semi-stable locus. Okay. So this is actually one of the last proposition I stated last time. I didn't give proof. I'm going to give the proof now. Okay. But what's interesting is that a converse holds. So conversely, if OX is closed in XSS and the dimension of the stabilizer is 0, then X is stable. Okay? So for points whose stabilizer is finite, the orbit being closed is enough to guarantee that it's stable. You don't need to check the orbits around that point. So let's show this proposition. The reductive assumption would actually be needed just for the converse statement. This one we don't need that. But let's put this together. So let's prove the first statement. So suppose that I have a point in the stable locus. Then we have the definition. So there is a homogeneous invariant polynomial of degree D such that X belongs to the principal open subset and the orbits in XF are closed. Okay, so that's straight the definition. And as we point out, we have that this is contained in the stable locus. Now, what I want to show is the following. I want to pick an element which is in the closure of OX bar inside the semi-stable locus. And what I want to show is that this Y is in the stable locus. So actually, we're going to show that f of Y is different from 0, because this would imply that y belongs to xf, and then here, so it belongs to OX bar intersected with xf, right? And the orbits are closed, so that's just OX. Okay? So it would imply that the orbits are closed in the bigger set XSS. Okay, so we pick this point. It's a semi-stable point. So that means that there is an integer and a polynomial, the same thing as before, well, almost the same thing, such that h of y is different from 0. Okay, because it's semi-stable. But it's invariant. So if h is non-zero on y, it's also non-zero on x. Right? Because if it would be 0 on x, it would be 0 on the orbit, it would be 0 on the closure, and that's not the case. So you see that both x and y belong to the principal open subset xh. And now we consider a regular function on this principal open set, given this way, as this quotient. Right? So it's a quotient of homogeneous polynomials of the same degree. Both of them are invariant, so this is invariant. What I'm saying? Yeah, so it's an invariant regular function. Right? And what we have is that f of x is non-zero, right? Because capital F of x is non-zero. And then f of x has the same value on the orbit because it's invariant, and also in the closure of the orbit inside x of h, right? Because it's where it's defined. But that's exactly where y lies. So we have that f of y is different from 0, just as this one, and then that means that f is different from 0. Okay? So that's the first part. Now let's look at the converse statement. So suppose that this guy is closed inside here. Suppose that the dimension of the stabilizer is 0. So this condition here. Since I'm picking my point is already semi-stable. Again, there are those polynomials. So there is this polynomial. Such that f of x is non-zero. Okay, so there is this polynomial. And since the principal open subset is inside here, and the orbit is closed in here but lives in here, then the orbit is closed here. Okay? So I put everything in box here just to point out that what we're going to use is actually these three here. Right? We're not going to use that this is closed inside the larger one, that it's closed inside here. And I point this out because we're going to use this weaker version of the theorem, of the proposition, twice in this lecture. Right? So what's important is that the orbit to be closed inside this principal open subset. It's so what we do, we consider the points where the dimension of the orbit is less than the dimension of G. Okay. And this is closed. So this is closed inside XF and invariant because the condition on the orbits. Okay. Moreover, it doesn't intersect OX. because OX has the maximum dimension, the stabilizer being finite. Right? So this is because the dimension of Gx is 0. Okay? So since we have a reductive group, we know that we can find an invariant function that separates these two invariant closed subsets. Right? Because OX is also closed. So there is a function on XF, which is affine, so I mean we can apply this, such that f of x is 1 and f of z is 0. Okay. And as I mentioned, something invariant. Now a function here is something of this form, where h and f are homogeneous. And in fact, since f is homogeneous, you can work a little more and get the numerator is homogeneous. In fact, this is a consequence of something we proved, or the exercise I left you at the end, which is simply the fact that the G-invariant guys here are, so here you have a localization, right? And then you're taking the G-invariants. So you can commute that. And so this is the G-invariant of the coordinate ring of the cone, or the variety if you want, localized. Okay. So if you use that, you can get this description of f, where the numerator is invariant as well. Okay. But then what we do, we let P to be h times f. So we're going to look now at a smaller open subset where P is non-zero. And you see that X is in XP inside XF, right? Because F is 1. So H is, what I'm saying? Yeah, F is 1. So both F and H are non-zero. And your closed subset is in the complement, right? Because H is 0 because of this. So you see that all orbits in XP have the maximum dimension. Maximum dimension equal to the dimension of G, right? Because I left out all the orbits which have smaller dimension. That's the definition of Z. And if that's the case, then all orbits are closed. In XP. Right? Because if you have an orbit that is not closed, then you look at a boundary point, and you look at the orbit passing through that boundary point. It will be contained in the boundary, but the boundary has the smaller dimension. Right? So what I'm saying here is that if y belongs to the boundary of some orbit in XP, so also in XP, then the dimension, then the orbit will also be contained in the boundary, and then the dimension would be smaller. Right? Which is not the case, because all orbits have the same dimension. Right? So that guarantees that all the orbits are closed, and I mean, that's what I need to get stability. So that tells you that XP is contained in the stable locus, and X is in there. Okay? Now this set of points, they are easier to deal with because we don't have to check all the orbits around the point. We just have to check that the orbit of that point is closed. Right? So let me give you a definition. So a point x in S xs is properly stable if, so a stable point is properly stable if the dimension of the stabilizer is 0. Okay? So you have S0, which is inside here, and as we mentioned, it's both open and closed. So these are the points that are easier to deal with. Sometimes there are all the points, sometimes there are none of the points, but, well, we're going to actually see some cases here. All right, so why they are easier to deal with? Because of this proposition. So, I'm in this setup here. I'm going to pick a point in Pn, and I will pick a lift of it in an plus 1. Okay? So x check is a representative of x in an plus 1. Then, if my point is in the stable locus, then 0, which is a point here, does not belong to the orbit of that x check, to the closure of that orbit. So remember, I mean, the representation is in Gn minus 1. So there is an action, not just on Pn, on an plus 1. So I can consider the actions, the orbits of this action. Right? So that's what I'm doing. And the other condition is that if x is in the properly stable locus, then the orbit map from G to an plus 1 that takes G to G check, Gx check, right? So that's above again, is proper. Okay. So these are just one direction, but the converse holds if G is reductive. Okay? So you have a characterization of semi-stability and proper stability, which is actually useful because of the conditions here. You can check these conditions using the relative criterion. Okay? So you can check this condition just by looking at curves. Yes? I mean, the orbit is closed, a condition on that. Uh-huh. Closed in the affine space. Well, it's going to be, right, if it's properly stable, because this map is proper, so it's going to be closed. Let me see. No, that's enough, actually. Just one moment here. Being closed. Now, being closed is not enough. No, I will say that it would be properly stable, but not. I mean, wait. I think. No, it's not enough. I don't know, actually. Okay, so let's prove this. Okay, so proof. So let's prove one. So again, it's a definition. There is this invariant guy. Such that f of x and then f of x check is non-zero, right? But since it's on the affine, I can actually compute this. So let me call this C. And the condition is that this is non-zero. Okay? So that's from semi-stability. But of course, F is invariant. And then what happens is that F of the orbit and of the closure of the orbit is the same C, which is non-zero. Okay? But since the degree is positive, this is a homogeneous form, it has to be 0 in 0. Right? So 0 does not belong to the set. Okay, so that's just that. 2. So, suppose in addition, suppose X is in XS, then there is F as before, but in addition, we have that the orbits in XF are closed. Okay? So it's the same condition. There is this C, non-zero, but again, this additional condition. In fact, we have also that since X, we have to assume more, right? We have to assume that X is properly stable, which says that the dimension of the stabilizer is 0. And now using that, let's consider the morphism phi of X from G to the orbit inside X of F. So let me compose with the inclusion here. Right? So what happens is that this map is finite. Okay, so why is it finite? Well, first of all, the orbit is closed. So this is just a closed embedding. Right? So what I'm saying is that this map is finite. But since the dimension of stabilizer is 0, all the fibers are finite. Okay, so that means that this map is generically finite. Right? But since the orbit is transitive, we do just as in the first proposition we proved. We take this open subset where the map is finite, and then we translate, and we cover the whole thing. Right? So then the map is finite. Okay? So that's just that. And now what we do, it's not, I mean, this map being finite, it's proper, but it's not what we want. We want this map here. So we have to compare them. And then I'm going to pick this closed subset inside the affine space. So the points in the cone such that f of v is C. Again, so it's a closed condition. And of course, I mean, my map phi check factors through Z. Right? Because F is invariant, and that's C is the value on X check. So now if we consider the map, the projection map, so Z lives in the affine space, but it doesn't contain 0, right? Because 0 would get F of 0 is 0. So I can consider the map from Z, the projection map, from Z. And where does it go? I mean, F is non-zero on Z, so it goes to XF. So this is just projection. Here I have my map phi check, and here I have my map phi of X. Right? So you have this commutative diagram, and what you know is that, I mean, everything is affine here. G is affine, Z is affine, this one is affine as well. And you know that phi of X is finite. Right? So when you look at rings, you see that this is that this ring here is finite over this one, and then it should be finite over this one here, because it's intermediate. Right? So that shows you that phi check is finite, and then it's proper. So that's what we wanted to show right here. Right? So let's look at the converse now. So conversely, suppose G is reductive. And let's look at the 1. So suppose 0 does not belong to the closure of the orbit. Right? And now you have the set 0 and the orbit. They are disjoint. And they are invariant, right? Because G acts linearly on an plus 1. It sends 0 to 0 always. Right? So these are closed, disjoint. So these are closed, invariant, and disjoint. So we know that there is a polynomial. So I'm looking at the action on an plus 1, right? So it's an affine variety, so I know that there is an invariant polynomial such that, first of all, it sends 0 to 0, and x check to 1. I'm sorry, this should be x check. It's right here. Yeah, here it's right. All right, so I'm looking at the orbit above in an plus 1. Okay? So there is this polynomial. It's not necessarily homogeneous. But of course, we can write it as homogeneous, as a sum of homogeneous, right? And since f of naught is not, I mean 0, then I can pick I bigger than 0 there. There is no constant term. Right? But then, I mean, if this is 1, it means that one of these guys is non-zero. So there is an I such that fi of x hat is different from 0. So there you have your, so yeah, since this is invariant, the homogeneous parts are invariant as well, because the action preserves the degree, right? And so there you have it. You have that x belongs to xfi, where fi is a homogeneous invariant polynomial of a positive degree. So that's semi-stable. Okay, so this is the converse to the first statement. You see that we use that property of reductive groups, the existence of this function, f. Now let's look at the second one. So suppose now that this map, phi check, is proper. Then, of course, then the image is closed. Right? Now x check is non-zero, right? And we're acting by automorphism, so that means that the whole orbit is not zero. I mean, 0 is not in here. And so 0 is not in the closure as well, because it's the same thing. So that already implies that I have a semi-stable point. Okay. So, again, there is that polynomial. Such that C, which is f of x hat, is non-zero. Okay? And then we do the same thing as before, right? We define Z, let me recall, the set of points in the cone such that f of Z is C, right? And we have this diagram there, the same diagram, right? Except that now we don't have this. What we have is this, by assumption. Okay? So you're getting the same diagram again. So now what you want to conclude is something about this map here. And a little exercise, if you haven't done that before, this map is finite. Which is kind of easy to see that at least it has finite fibers, but it's actually a finite map. Right? So that has nothing to do with group theory. It's just, the way it is. Right? So this is a finite map. And so you have a finite map, you have a proper map, right? Then the composition is proper. So phi of x, which is the composition phi check, both proper maps. This is proper map. Okay? Now, being proper means that the fibers are complete. But this is affine. The fibers are closed. So the fibers are also affine. So the fibers are affine and complete. So that means that they are finite dimension. So that means that the dimension of the stabilizer is 0. Right? Because the fibers are isomorphic to Gx. Okay? So there is a but here. So the fibers are finite. And that means that the dimension of the stabilizer is 0. But now we're done because, also because the map is proper, we have that the image with OX is closed. So we have that the image is closed in here. We have that the dimension of the stabilizer is 0. And that's that proposition I told you about that I wanted to use part of the proof. Right? So these two conditions and imply that X is stable and then properly stable because the dimension is 0. So remember that first proposition that we stated that if the orbit is closed in the semi-stable locus, then these conditions would be enough. But in the proof, we saw that we just needed this. And that's what I'm using. Okay? All right. So as I said, this criterion tells you that to check for semi-stability and stability, you can use the relative criterion. That is, you can consider curves. Right? Just look at curves. And in fact, what's more striking is that you need only to look at very special curves, which come from one-parameter subgroups. And that's quite striking. So let me define this. So let me leave this there. So definition. So let's consider the multiplicative group of the field, Gn. So that's GL of 1, which is just A1 minus the origin, so it's a curve. Okay. Then we say that one parameter subgroup of G, so of an algebraic group G, is a non-trivial homomorphism of algebraic groups lambda from Gm to G. Okay? So that means that the image is a subcurve of G. And that's the kind of a subcurve we're going to actually need. So what can we do with a one-parameter subgroup? We can define a numerical invariant associated with a point x in X, and with the action of the group, of course, in the following way. So we pick a point in X, right? we pick a lifting of that point. And then we can consider the action induced. If we have a one-parameter subgroup, we can consider the action induced by this one-parameter subgroup, and then the orbit of this point x check by this. So this is lambda of t that lands in G, and then we apply this to x check. Okay? So what we have now is a collection of functions of t, right, that are defined in this, the affine line minus the origin. So we know what these kind of functions look like. And in fact, they are rational functions whose denominators are powers of t. And so we can organize all of these in the following way. So you see that there is a unique integer mu, unique, and f naught, f, n polynomials, such that one of them is not divisible by t, or some I, right? And such that I can describe this guy in t as 1 over t to the power mu f naught t up to fn t. Right? So, I mean, all functions are of this form, like fi of t over a power of t. So organize them in this way. Right? This is a unique way of doing that. So you have this integer here, mu. Just notice that by linearity, if I pick a different representative, right, I'll be acting on c times x check, but this is linear, so I can drop c to the outside. So this is this for c non-zero, right? And it's a constant, so it doesn't change the value of mu. It's the same mu. Right? So I can define mu x lambda and not x check as this mu. Okay, so given a point on x, or even on Pn, but we consider on x, and a one-parameter subgroup, I have this integral associated to it. Right? That is defined in this way. And now it comes the I will pass over here because I want to leave this criterion somewhere. I'll leave it here. Leave this for comparison. And then we have the theorem, which is the Hilbert-Mumford criterion. So Hilbert knew that for the action of SL, SLN, which is the following. Similar to here, if x is semi-stable, then this mu is always non-negative for every one-parameter subgroup lambda of G. Okay, so I'm going to use this shorter, 1PS. One-parameter subgroup lambda of G, mean all of them should be non-negative. And if x is properly stable, then they should actually be positive. And conversely, we have it holds if G is reductive. Okay, so that's what I was saying. I mean, here in principle, you'd have to apply the evaluative criterion to have to consider curves of all kinds, or at least infinitesimally. But in fact, you just need to consider curves that arise from one-parameter subgroups. Okay. So I won't give the full proof of this. You can find in, in the book by Mumford, he uses other results from group theory, or you can find in the book by Newstead, an elementary proof for SL, or G is equal to SL of M. Okay. So it's an elementary proof, which for a lot of purposes it's enough, because most of the times in applications the group that appears is SLM. What I'm going to do is just to try to show you the connection between these two. Let me just show this one here. And you're going to see how things are actually related. In fact, you can show 1 and 2 very easily. There's no problem here. It's the application, the converse, that you have to use special properties of reductive groups. Okay? But let's show 1. So what we're going to do is we're going to pick, we have an X, which is semi-stable. Let's pick a representative above X. And we consider phi, again, G to AN plus 1. That takes G to G X check. Okay, so we pick now a 1-parameter subgroup of G. Then we have that expression. Right? And remember that this is simply composing this map. So let me put here. So lambda x check is simply the composition of phi with lambda. Okay? So everything here lies in the orbit of x check. Okay? Now, if this has a negative nu, right? So what happens is that everything becomes polynomial here, right? And more than that, we have that lambda x check tends to 0 with value 0, right? Because q minus mu, that's 0 on, and everything else is polynomial. Okay? So that tells you that since 0 is the limit of those things, that tells you that 0 belongs to the closure of this orbit. And that means that, as we showed there, that the point is not semistable. Okay? So you see the connection quickly. 2 is very similar. So I'll leave this as an exercise. 2. And as I said, the converse is not an exercise. It's a difficult statement. And I don't have time to prove because I want to move to the last part of this course, which are examples. Okay. So I want to show you how you can apply this criterion to actually describe in some situations what are the semi-stable and properly stable points. So what you're taking quotient of. So we need some results before we go to examples. First of all, we need a structure theorem on these 1-parameter subgroups. I will do that just in a simple case. In fact, I mean, since every group is inside GLN, so for some n, I'm basically doing a more general thing, but let's leave it at that. So let's consider a one-parameter subgroup of GLN. Okay. Then the statement is that there are G in GLN and integers L1, Ln that I can organize as I please, and I will do it that way, such that lambda of t is the conjugate of a diagonal action. Okay? So up to conjugation, one-parameter subgroups are very simple. I won't show this. It's not that difficult. It just takes a bit of time, I think. What happens, of course, what you use here is that the GM is commutative. So all these matrices that appear here, they commute with each other. So in a sense, you use that you can, if you can, diagonalize them simultaneously. Okay? And that's basically what we're doing, right? We are diagonalizing simultaneously with the same conjugation all the lambda t's. No, I think you need something more. Yeah. You need something more. No, not that. As far as I remember, as I said, Mumford doesn't really give the proof. He uses some results and still builds on that to get the proof. As far as I remember, I'm not so sure. I have to check that. Okay, so I'm not going to show this because I want to pass to the examples. But that's an important result to use. And another, which is just a remark, which is equally as important, is that we're interested in these integers. We're interested in one-parameter subgroups that are conjugate to a given one. And this integer is the same thing as the associated integer of the translate. So this is just a remark because what you have is that if you look at the action of these on some x hat, then you can write in this way. Right? So mu is the power that appears in the denominator of this expression, this mu, right, is the power that appears here. Since G is constant, and it's an automorphism, when you do that, you get the same power, right? And over here, the power in the denominator is this mu here, right? So the fact that G is constant and an automorphism tells you that the power is the same on both sides. So let's see how to apply this to classical stuff. So let's now look at V be a vector space over K, always algebraically closed, right? So we have that the special linear group operators with determinant 1 acts on V. So on K of V and on K of V n for every n. Okay? So we have seen that. So what we are interested in is in the action, not in here, which is kind of trivial, but on here. Right? So the action of this in this subspace and actually on P of KV. N. Okay? So we have a projective space, and what's this parametrizing? This is parametrizing hypersurfaces of degree n in the projectivization of V. Okay? Let's look at the special case of binary forms, which is the case, I don't need any more. Let's look at the case where the dimension is 2. Then in this case, I have polynomials in 2 variables, homogeneous ones, and then we know that since we are over an algebraically closed field, that it decomposes. So it's the product of n linear factors. Right? Some of them might appear with multiplicity, might appear repeated, and that's what's going to tell us whether this f, or rather the corresponding point in the projective space, is semi-stable or properly stable. So, proposition, assume dimension of V equals to 2. Then, the corresponding point in the projective space is properly stable or semi-stable if all the linear factors of f have multiplicity less than n over 2, or in the case of semi-stability, we don't need to be so strict, less or equal than n over 2. Okay? So just look at the decomposition. I mean, if there is a linear factor appearing too much, then it's not semi-stable or it's not properly stable. So let's show this. Okay, so I don't need this part here anymore. We're going to use this here. So proof. So we choose a basis for V and a dual basis. X0, X1 in V dual. So I'm going to look at homogeneous polynomials on X0 and X1. Let's look at a very special one-parameter subgroup, right? We chose a basis already, so I'm going to look at lambda t of this form here already. Right, so it's dimension 2, right? So it's a 2 by 2 matrix. And if I want this to be in SL2, I need that the determinant be 1, so I need that L0 plus L1 is 0. And if I want this to be non-trivial, then and L0 greater than L1, so I have this. Okay, so let's consider one-parameter subgroups of this form. They are non-trivial. And let's write F as a sum of monomial terms and see how the action is given. So that's not. Right, so my projective space here is actually Pn, right? That's the coordinates of F are A0 up to An. And the action is the action on F. Right? Remember that when we defined the action, we took the inverse. Right? And so, what we have here is the following. So you see that on monomials, the action of lambda t is also diagonal. right? So we have that this is t to the power minus n L naught. The minus comes from this minus 1 here, plus t of minus n minus 1 L naught minus L1, A1 x naught n minus 1 x1, plus, plus, plus. Right? And at the very end, we have t to the power minus n L1, an x1 to the n. Right? So I hope that this standard is clear. But now we use that this holds. Right? So one is actually given in terms of the other. So I can write f lambda of t to be t of minus L naught, A naught, x naught, n, plus, see, L naught plus L1 is 0. So this is the same thing as t of minus n minus 2 L naught, A1, x naught, n minus 1, x1. And it then goes on like that. You see that I'm subtracting, or actually summing 2 L naught at each term. And at the very end, I get n L naught, an x1 to the n. Okay? So you see that we're dropping by 2 L naught every step up until here. So that's the action, very easy to describe. And now, you see that mu of that point corresponding to f and with respect to this semigroup is less or equal than 0. That's, I mean, I'm doing the opposite here, less or equal and less. Right? So, and respectively less than 0. If and only if the coefficients of f lambda t. So mu, remember, is the power of the denominator. So it's less or equal than 0. That means that you have polynomial things. So if and only if the coefficients are polynomial in t, and respectively, and 0 for t equals to 0. So there are polynomial in t. And if it's less than 0, 0 for t equals to 0. And then you check the expression here. You see that L naught is positive. So these are all negative powers of t until you get to a point which is more or less half the way where you reverse. And you start getting positive powers. Right? So this is if and only if ai is equal to 0 for 0 less or equal than I less than n over 2, right? And if I want to be 0 for t equals to 0, I have to add, if necessary, n over 2. Okay, so if n over 2 is an integer, what happens here is that you have no power of t. Okay, which is okay in this situation, but for here, not. You have to remove that one as well. Okay? And this happens if and only if x1 is a factor of f with multiplicity at least n over 2 or respectively greater than n over 2. Okay? So as you see, I'm removing, right? So these coefficients, and then you have a high power of x1 dividing f. Okay? Okay, so for this particular lambda, that's the linear factor that appears with high multiplicity. But then we're going to use this remark here to have it more general. So, now let h be a polynomial of degree n. right? Suppose that there is a linear factor with multiplicity greater or equal than n over 2, or greater than n over 2, right? So I'm looking at this statement there. So this, yeah, right? So I'm looking at this condition here, the negative of that, actually. So suppose that, then, of course, there is a G. There is a linear transformation such that x1 is such a linear factor for the polynomial f hg. Okay, so you take the translate such that this linear factor becomes x1. Yeah? And then what you see is that x1 is a factor with multiplicity at least n over 2 or higher than n over 2, and then that implies that mu of f lambda is less or equal than 0 or less than 0 for lambda of this form. Okay? But that implies then that since there is such a lambda, right, which, so not all, I mean there is such a lambda, then that implies that f is not stable. And respectively not semi-stable, right, because it's less or equal, so not stable, not actually properly stable, and not semi-stable, but H is in the same orbit as G, so it has the same properties. So the same thing. Okay? And conversely, so conversely, if H is not properly stable, respectively not semi-stable, then by the theorem, so by Hilbert-Mumford, we're using it another time, there is a lambda, right? Let me put it that way directly. Diagonal, so of the form that I put in here, such that mu of H G lambda G inverse is less or equal than 0, or respectively less than 0. So now there is a lambda diagonal and there is a G in SL2, the conjugate, such that this happens. Okay? Right? So this is the form, from that proposition, this is the form of a general one-parameter subgroup. Right? But then we use the remark, this is the same thing as mu of hg, or actually I have to put g minus 1 and g here from the remark. So that's the same thing as mu of hg lambda. Right? So lambda diagonal of the form that we had before. So then we can now use this thing here and say that x1 appears with multiplicity. So that means that x1 appears with multiplicity, at least n over 2, in my polynomial, which is hg. Right? But if that's the case, then x1 translated by g minus 1 appears with the same multiplicity in h. And that's what we want to show, that there was a linear factor appearing with this high multiplicity, because we are negating everything here. Okay? So that's how you can use it. In fact, this is a very simple situation. So let me do it but it was good, to see the criterion be applied. Let me do it something a little more interesting, but it's still basic. Let's suppose now that we are in dimension 3. And let's pick f in degree 3. Right? So what we're doing here is we're picking a plane cubic now. And then the point in here, I'm just going to do the properly stable case. And that's the case if and only if the cubic is non-singular. Okay. You can also check semi-stability. In fact, the cubic is going to be semi-stable if and only if the curve has no triple points and no double points with common tangent. Okay. So that's what you get. But let's do just this case. So we do exactly as before. We're going to pick a basis of V, a basis of the dual, and we're going to first consider lambda t of a special form. So now it's a 3 by 3. So we have one more power. We can organize in this way. It must be a one-parameter subgroup of SLV, so we need the sum to be 0. Right? And then what you see is that L0 has to be positive, and L2 has to be negative, and no conditions on L1 necessary. Okay? So the third condition follows from the first two. Now I'm going to write F, and I'm going to write it in a particular way, which is very useful in this theory, which is in triangular form. So there is a coefficient here, right, A0, plus, let me put A here. So plus b x naught square x1 plus c x naught square x2. So now there are 3 variables. So here the cubic power, the square power, and then we move on. Plus d x naught x1 square plus e x naught x1 x2 plus f x naught x2 square plus g x1 to the cube plus h x1 square x2 plus I x1 x2 square plus j x2 to the cube. Didn't state too much triangular, but okay. Right? So these are A, B, C up to J. These are the coordinates of this point in the projective space. And then what I want to do is, and I want to do it here because I don't want to draw this again, is to apply lambda t. Right? Remember, to apply lambda t, we have actually to take the inverse and then apply. And you see again that the action becomes diagonalized by these monomials. So what I'm going to have here is t to minus 3L0. Here we're going to have t minus 2L0 minus L1. Here will be t to minus 2L0 minus L2. T to minus L0 minus 2L1. T to minus L0 minus L1 minus L2, which is actually 0. Plus t to minus L0 minus 2L2. Here I need some space. T2 minus 3L1, T2 minus 2L1 minus L2, T2 minus L1 minus 2L2, and then here T2 minus 2 L2, minus 3L2. Okay? You can actually do this for higher degree, and that's actually what Mumford does. If you look at the book, he does for quartics as well. I mean, for cubics he actually doesn't do, but he does for quartics and then states the results for quintics. Of course, it becomes more complicated, but it's doable. Okay, so what we want to do now, so let's try to prove this statement. So let's consider some h in P. So let's consider a cubic. Suppose x is singular. So I want to show that the point is not properly stable. Since it's singular, then I can move this singular point to this specific one for a translate, which I'm going to call by f, for some g. Okay, so now I have a polynomial, which is the f I'm writing here, the sum of, what I wrote before, right? And this point is singular, so that implies that a equals to b equals to c equals to 0. Right? So a equals to 0 for the point to belong to the curve, and b equals to c equals to 0 for the linear factors to be 0. Okay? Now, I want to show that the point is not properly stable, so I want to find a particular one-parameter subgroup, right? Such that mu is non-positive. Right? And that's what we're going to do. We're going to pick a lambda like that with L0 equals to 2 and L1 equals to L2 equals to minus 1. So it's not just any one-parameter subgroup, but that one works. Because if you do that, then you start looking at the coefficients, at the powers here. So this power is 0. This power was already 0. This power here, again, is 0. It's the same as this one. This power here is 3, right? Just as these ones here, 3, 3, and 3. So you see that everything here is 0 because of the singular point, and all the powers here are positive. So that means that the mu, which is the power of the denominator, is non-positive. Okay, so this is polynomial in T. So that means that the power of the denominator is less or equal than 0. And then that's the remark I mentioned, since f is hg, then that implies that mu is non-positive for this one-parameter subgroup. Okay, and then h is not properly stable. Okay, this is one direction. So conversely, so suppose H is not properly stable. Right? So we use the criterion here, and what we know is that there is a G and lambda of the form star. There is of this form here, right? So every one-parameter subgroup is a conjugate of this one, right? So I have a G and a lambda such that mu of H G minus 1 lambda G is non-positive, or what's the same thing, mu of F lambda is non-positive for F is equal to HG. Okay? So let's look at this F. Let's write this F in this triangular form, and let's apply lambda T. So the coefficients must be polynomial, since this is non-positive. So the coefficients of F lambda T are polynomial. So let's see how that can be, right? Because L naught is positive, so this is not polynomial for sure. So I need A equals to 0, right? So the first thing is that I need A equals to 0. Let's look at the power that appears next to B. It's minus 2 L naught minus L1, but minus L naught minus L1 is plus L2, right? And this is negative because L2, this is positive. But no, it's negative. L2 is less than L naught, right? So that means that B must be 0 as well. Now let's look at C. Now here we have something that, okay, we don't know, right? It depends on lambda because minus 2 L naught minus L2 is minus L naught plus L1. And then the only thing we know is that L1 is less or equal than L naught, so this is less or equal than 0. It could be 0. Right? If it's non-zero, that is, if L1 is strictly less than L naught, right, then C must be 0, and then we get a singular point. That then finishes because then we have a singular point for H as well. Right? Now, if you have equality, then let's see what happens. Now I'm going to move to here. So L naught is equal to L1. So, yeah, I guess that's enough. L naught is equal to L1. So you see that here we have minus 3 L naught, which is negative. And here we have also minus 3 L naught, which is negative. L naught is positive, right? So all these powers then become negative, and then the coefficients there must be 0 to get something polynomial. But then, I mean, all this diagonal is 0. That means that x2, x2, that x2 divides f. So again, f is singular. Okay? So in any way, you have a singularity there. Okay. So I want to finish with a more general result, but let me just make a remark here. Before that, another remark is that, of course, there are non-singular cubics. So that means that there are properly stable points. And since we're dealing with an irreducible space, the projective space, there are no other stable points. So all stable points are properly stable. Also for binary forms. I mean, there are binary forms that don't have that high multiplicity. So it means that all stable binary forms are properly stable. Except in degree 2. We're going to see that soon. But the remark that I wanted to make is that GLV acts on V. So why SLV? So why do we consider SLV instead of GLV? And it's very simple because you see, I mean, you have the diagonal matrices inside GLV and also in SLV, but for GLV, any element of K will do. Okay, so let's consider an element of K inside GLV diagonally. Okay, and then what you have is that if you pick a polynomial of degree D, so what will be the action? I mean, there is an action. So what's the action of F on C, of C on F, right? So this is simply F C minus 1 of X. And since F is homogeneous of degree D, this pops out like this. Okay? So that's the effect of this action, multiplication by this matrix. Now, if we pick a homogeneous polynomial, so we're interested in invariance of the action on here. So let's look at a polynomial on this vector space. Okay? And let's look at a polynomial of degree n. So again, we have an action of GLV on psi. So let's look at what this action is. Again, the definition is that I put it inside, but I take the dual, the inverse, FC inverse. And then I use this, right? This is psi of C to the power df. Okay, so it's just multiplication by that constant. And then I use the fact that it's homogeneous of degree n to pop this outside. Okay. So you see that depending on the C that you choose, this is not going to be non-zero. This is going to be different from 1. Right? So there wouldn't be any invariant. Right? So invariance under GLV is very rare, actually. Right? It's, I mean, it's impossible in this situation. Right? Because you can choose a C such that this power is different from 1. In fact, even if you're restricted to SLV, so if C to the dn of is different from 1, then you see that psi is not invariant. Right? But if we are in SLV, say that the dimension of V is m. I haven't used that. Then we have that C of m is equal to 1. Right? And then, I mean, for this to be 1, it's you need that m divides d over n, d times n. So if so psi is not invariant unless, so invariant under SLM, unless SLV, no? M divides d times n. Okay? So that gives you actually a condition on the degree of the invariance. So the n that appears here cannot be just n. N times d must be divisible by n. So it's a necessary condition, right, to be invariant. And then you can show that there are invariants of that degree, but that's another matter. But let me just put here that what you have, if this situation holds, then since the determinant of C is C to the m, what you have is this. Okay? So if m divides d to the d times n. Okay? So people say that if you're looking at the action of GLV, I mean, you can do that as well. And then what you have is a relative invariant of this degree here. Okay? So that's what people worked actually in invariant theory. They worked with the action of GLN, and they looked at the relative invariance. And the determinant would always pop out, the determinant of G. In this case it's C, but in general to be G. Okay. But with our setup, that's why we look at SLV in most situations instead of GLV. So let me finish with a general statement. So you might ask, I mean, well, what was this business of properly stable and semi-stable? I mean, I want to look at plane curves, and I want to look at the plane curves I like, or to the hypersurfaces I like, and not this funny business given by this criterion. Well, at least you have some hypersurfaces that are interesting. So what I want to show is the following. So let's look at a hypersurface of degree d on a general projective space. And if that hypersurface is such that the degree is at least 3 and f equals to 0 is non-singular, then this point is properly stable. So at least you have all non-singular hypersurfaces in your quotient. Okay? So let's give this proof. First of all, we consider the discriminant. D is a homogeneous polynomial in the ring of functions on KV of D. Okay, so you have a homogeneous polynomial whose degree depends on D, such that D evaluated on F is non-zero if and only if f equals to 0 is non-singular. Okay? And it's actually an invariant here. Okay? So if I have time, but I don't think I will have, I'll explain how this polynomial is obtained. But it's the so-called discriminant. It's a classical object. Right? And it characterizes when f is non-singular. Right? And it's homogeneous, so that if f is non-singular, then the point is semi-stable. Right? So that's my x now. Okay? The action is by SLV, as in all the past examples. Right? So you have an invariant polynomial that does not vanish on f, so you see that f is semi-stable. Okay? So let's move on. So what we need to show now, and I'll explain why, is that the stabilizer of f of this point is 0. If we show that, we finish. Why is that so? Because of course, I mean, if d is greater or equal than 3, and you're going to see the condition appearing. So why do we need? Why is that enough? Okay. So what happens if this is true for any non-singular f? Then that would imply that the orbits in XD, this principal open subset, they have maximal dimension. Right? So the points in XD are corresponding to non-singular hypersurfaces. And if all of them have this dimension of the stabilizer 0, then that means that the orbits have dimension equal to the dimension of the group. And then we see that each orbit is closed. that's the same argument as before. I mean, if there was something in the boundary, the orbital would have smaller dimension. Right? And then what we have, the orbitals are closed in here, and the stabilizer is 0. So that tells you that F is properly stable. So it's that proposition, again, used in this weaker form. That is, if the orbit is closed in this principal open subset, and the dimension is 0, then you have a properly stable point. Okay? So it's just a matter of looking at the stabilizer. And how do we do that? So it remains to show this. It's enough to show, or equivalent if you want, but it's enough to show that the tangent space so this is a subgroup, so there is the identity in there of GF is 0. Okay? So the dimension is bounded by the dimension of the tangent space, so that's 0, then we're done. Okay? So how do we do that? Well, we use the infinitesimal description of the tangent space, just like Bertrand did last week. In fact, last week, I mean, this, of course, I mean, this lies inside the tangent space F at the identity of the whole group. And Bertrand showed last time that this can be identified with the set of matrices whose trace is 0. Okay? And to show that, he used the infinitesimal description, and that's what we're going to use to show that the tangent space is 0. So what we're going to use is an infinitesimal deformation of the identity. Right? Where epsilon square is 0, and this is a matrix, which we already know, actually, to be in here, then that matrix has to be trace 0. That's what Bertrand showed. Right? But what does it mean to be in here? It means that when I modify it, right, I should get the same F again. So let's see what this is on this side. On this side, so that's simply F of x plus epsilon ax, and then we use the Taylor expansion around x, so that's Fx plus the epsilon pops out, and I have to take the derivative. So it's the derivative at x, right? So it's this times, so the sum over i's times the derivative of the ith component here of this product. And that's the summation of aij xj. So it's no, it's more simple than that. I mean, it's Taylor expansion. Okay. Of course, I mean, when you expand, you're going to have something else, but then epsilon square appears, and epsilon square is 0. Right. So what we have to show to have equality is that whatever is in here is 0. Right? So we need, to have that this deformation here lives in here. So to get a point in that tangent space there, we need this summation to be 0. Okay? So let's look at it in another way. So that's the summation over I of the summation ij xj. And then here this. Okay? So you have the derivatives here, and you have a relation between them given by these linear forms. So you need this polynomial to be 0. But then your hypersurface is non-singular. And that means that the 0 locus of the derivatives only at the point 0. Okay, so you have n plus 1 hypersurfaces cutting something of a codimension n plus 1, and that implies that you have a regular sequence. So that's something commutative algebra. And what you have from that is that the only relations are the trivial ones. Or multiples, or sum, or combinations of the trivial relations. And by trivial relation, I mean something like that. So these are the coefficients. Okay? So, of course, this is 0. And what happens is that you vary I and j, take sums of these, and these are the unique relations that you have. Okay, but here I have a relation which involves a polynomial, polynomials of degree 1. Right? So if these guys are non-zero, then I need them to be multiples of the trivial relations. That means the degree of this should be greater or equal than the degree of the derivative. Right? So that's d at most 2. And we are assuming that the d is at least 3. Okay? So that shows you that all these aij must be 0. And that finished the proof by showing that the tangent space is trivial here. Okay? So, if I have time, one last statement. What happens for degree equals to 2? So for degree equals to 2, you're looking at quadrics, right? And what happens is that in this situation, the discriminant that parameterizes then the non-singular quadrics is the same thing as the semi-stable locus, which is the same thing as the stable locus, but the properly stable locus is empty. Okay? So they're still stable. They're not properly stable. Okay? So the dimension of the stabilizer is non-zero. Yeah, that you can show easily. You can just compute dimensions if you want. Okay,